The fact that a consistent maintenance program is necessary and mandated goes without argument, but every FBO can relate horror stories of occasions where the need for maintenance has been overlooked. The very minimum is the required annual inspection. 100-hour inspections required for revenue flights are more timely, but many knowledgeable owners adopt a progressive program, which in conjunction with qualified help will serve as preventive maintenance. In effect, it is a continuous inspection done in small increments. This should reduce the charges at the time of the annual inspection. The best estimates we have seen on man-hour requirements for a complete annual inspection on an airplane that has the logbooks in good shape is 19 hours, if the owner has not participated in the inspection with the repair facility. We certainly do not propose that you rush out and spend next year's lunch money on a pile of tools and lotions for removing grease from your hands. We do believe you should become sufficiently conversant with the workings of your airplane to effectively oversee your maintenance program. You should know that FAA regulations allow 28 maintenance functions to be performed by pilots, with the caveat that the work be approved by an A&P mechanic or an approved repair station. This is called owner-performed maintenance or preventive maintenance. If you are interested, we refer you to Appendix A, Section C of Part 43 of FAA regulations. Several places offer short courses in this activity, and we have a very inexpensive tape that teaches the most important procedures. We suggest that you form a partnership of sorts with your local fixed-base operator in the maintenance of your airplane if you decide to go this route. This person will very likely be as interested as you are in keeping your costs down and may welcome your increased capability to report service difficulties. In spite of a few bad apples who have tarnished the business, the average FBO is the backbone of general aviation and is driven by the desire to have you be happy with your airplane. In this tape, we discuss problems that are often generated by the bad apples. Throughout this tape, we will refer to SDRs, or Service Difficulty Reports. These are reports filed with the FAA by maintenance people, FAA agents, and pilots. They detail recurring problems which were dangerous and costly because they were allowed to progress from minor to major. We have screened a 2-year history of these reports and grouped them in areas where, in most cases, an observant pilot could have made a safety difference. As we begin, let us assume that you have elected to exercise your right to remove the cowling, and we will conduct a system-by-system briefing. We will, from time to time, interject some discussion relative to the SDRs and corrective action, as well as some comment on flight techniques. This briefing is concerned with those aircraft powered by Lycoming engines. These are normally aspirated, meaning that the air pressure for the carburetor intake depends on density altitude, and available power will decrease with altitude. The engines are designated O320, the O for opposed, and 320 for cubic inch displacement. We will not deal with the Continental O470 engine, which powered earlier models in this presentation. We will start with a look at some possible problems that might be encountered in flight. We will look at the cockpit and examine closely those operational functions controlled by the pilot, what happens when systems are activated, and what an observant pilot can do to spot and correct incipient problems. A minor problem in an airplane is not like a minor cold in a person. Left untended, the cold will go away, but a minor problem in an airplane may quickly deteriorate into the aircraft equivalent of double pneumonia. Our only assumption is that you are a pilot interested in more safety and less cost, and want to be able to know enough about your airplane to report discrepancies and fly it efficiently. Let's look at a little bit of the accident background of the 172 and a few areas that might cause problems now and in the future. We should point out that the scenarios we have chosen here are usually worst case, but with a little forethought are easy to avoid. It doesn't take much skill to fly safely, but what it does take is knowledge to know what to avoid. We have studied over 13,000 accident reports over a 3-year period, and are happy to report that the 172 comes off very well. When one addresses the rate of fatalities per 100,000 hours flown, The 172 is very nearly the best in most categories in comparison with other general aviation aircraft. The airplane is simple to fly and ideal for the non-professional pilot. On the basis of any comparison standard, it would have an outstanding safety record. We attribute this in part to the rather heavy elevator forces of positive stability that make it difficult to approach a stall or spin without some effort on the pilot's part. When the speed is slow, the nose wants to go down. When fast, it would prefer to be going up, and the controls are heavy. Since the 172 is approved for spins, let's discuss them for a moment. Only the utility category airplane with no people or baggage in the rear area is approved for this maneuver. It follows that center of gravity and loading must be important when we consider spin practice or any other time we fly. Although research has been going on into spin entry and recovery since Wilbur and Orville, stall spin accidents still have not been whipped. The research aircraft in these pictures is a typical general aviation aircraft flown by a highly experienced test pilot. And as you will see, even he needs help, never available to the rest of us. The tests were done with fore and aft CG. In the first one, the CG is forward in acceptable range. Our second sequence has the CG far aft of an approved range. You will note that the entry was normal, but as the spin progressed, it began to flatten out, and by the 8th turn, the pilot could have been in trouble. In this case, he was able to make an unassisted recovery. The flat spin sequence with the aft CG shows a pilot's nightmare. The elevators are totally ineffective, and recovery without the tail chute would be only a matter of luck, which is known to be remarkably indifferent in this situation. The test pilot accepts money for this job and secures the benefits of a parachute for himself and one for the tail of the airplane. Otherwise, we suspect, he would rather be out fishing. We would bet that he doesn't spin airplanes for recreation. Every pilot should know how spins occur, how to recognize imminent spin indications, and how to avert a spin at that point. And every pilot should have knowledge of recovery. But these tools should come in concert with a planned and approved course of instruction with an expert. These sequences highlight the need to keep the center of gravity in an approved range. This should be true at all times, but it becomes critical when the airplane is being pushed to the edge of the operating envelope. You may be assured that a far aft CG makes a difference in the flight characteristics of the 172, and will make the person who toys with this configuration an unpaid test pilot. In fact, the normal spin characteristics of the 172 are rather benign. With the introduction of the 172L, and for later models, the dorsal fin was extended forward, and it is difficult to get a clean rotation without using unconventional methods. A normal entry technique may produce a wallowing nose-down turning moment to the right, and a nose-down spiral to the left with an unacceptable speed buildup in either direction. This speed buildup is serious. The extreme nose-down attitude will have the airspeed approaching VNE while the pilot is contemplating the situation. Each second will magnify the problem and limit elevator pressures to be used in recovery. The worst configuration imaginable for degrading spin characteristics in this airplane would be a venture outside the utility category with passengers in the back seat and, to ensure graduation from dumb school, lowered flaps. If you are lucky enough to recover, it is almost certainly guaranteed that you will never try it again. A fairly common accident cause is overshooting a turn and trying to correct to the desired point with back pressure and steepening. This combines the worst of all worlds. The steepening bank and the G-loads imposed by back pressure can be excessive. If the back pressure is violent enough and the controls are crossed, the airplane may try to snap into a spin. In the 172, this may translate into a downward rotation which has most of the bad characteristics of a spin and a few of its own. An approach to final is no place to start spin practice. The procedure when you overshoot a turn badly is to say, oops, level the wings, apply the power, build some airspeed, and enjoy the scenery as you fly around the pattern again. The best cure for problems with spins and imminent spins is to avoid them completely. The positive pre-stall indications inherent in the design of your aircraft, which you were taught on your checkout, should work as a red flag. Unfortunately, they are sometimes ignored in a stressful situation. The high speed range also seems to require some attention on the pilot's part to get into an awkward attitude in normal operations. Why, you may ask, do we have to worry about high-speed problems in an airplane not noted for high speed? Because a combination of factors has raised our concern. Some pilots have felt the heavy positive stability characteristic is excessive and have sought to dampen it by changing the elevator cable tension. The problem with this is that if the tension goes outside an approved range, you are flying an uncertificated airplane and have now become a test pilot. It is possible that flight test work has not been done, and we do not know where speed variances may take you. As the population of 172s has aged, some aircraft owners have relaxed maintenance standards, as some of us do in our old cars. This has resulted in a proliferation of potentially dangerous problems which we found in our samplings of the SDRs. We will discuss a few of these. Although in-flight failure has not been a major problem thus far with this airplane, we should touch on this area. If you were able to own a new airplane, fresh off the factory floor, you would have little immediate concern about this problem. The inherent stability characteristics and the high drag rise with increased airspeed have saved many pilots and passengers. Now age and sometimes carelessness has added another factor to the equation: corrosion. The latest 2-year study shows an alarming number of findings of control and corrosion problems. The following SDRs are only the tip of the iceberg. Quote, removed both wing tips to inspect wing, found rib at station 190, right wing, badly corroded. Removed leading edge of both wings, found large areas of corrosion on both skin and ribs. Left wing also inspected, found rib at station 172 corroded, and large areas of corrosion on skin and spar, unquote. Corrosion is an insidious hazard, and aluminum alloy is a perfect factory for this thief of strength. Unfortunately, oftentimes it is not readily visible, and by the time it is discovered in what may seem like obscure areas, it has created danger. Any airplane in an environment where moisture and air may combine with metal is at risk. This FAA map highlights the areas of most likely problems: inadvertent penetration into turbulent weather, attempted acrobatics, a sloppy spin recovery, or a simple buzz job on a friend's house all offer possibilities for finding that the strength factors of 3.8 G plus a 50% cushion we have felt so comfortable with no longer exist. A VA speed that assures us of safety with a full control deflection may now be unknown, but may be quite a bit lower. Intergranular corrosion may have damaged the spar, the control cables, the flaps, and other vital elements of safe flight, and opened the door to a possible frightening experience. When one works at it, it can happen, as this accident report of a 172M attests. Quote, VFR low-time pilot departed into area of severe thunderstorms. Aircraft lost wing in flight by exceeding load factors, unquote. So let's be careful out there, folks. Watch those high-speed excursions as carefully as you watch those at low speeds. The best bit of preventative maintenance you may ever start should now be under consideration. The first step would be a thorough inspection for corrosion. A likely indication might be white deposits of aluminum oxide, a white powder, on surfaces at points where metals join. A type known as filiform corrosion may be found under painted surfaces and other places. This appears to be the work of a multitude of tiny worms burrowing under the surface. A few of the areas that might be a source of worry are the carry-through section above the rear seat, the skin surface, the front and rear spars, the bottom rib of the vertical stabilizer, and behind the rubber panels on the cockpit side and floor. The next step would be to install a corrosion control program using modern materials which have improved the process a great deal. Many shops have adopted a protection program which involves spraying. We are advised that the process can be done while you wait, and small spray cans can be purchased which will allow the owner to handle spot treatments himself. The treatment supposedly lasts about 18 months and is reported to be superior to any previous method. We suggest you find someone who has had this treatment and get the first-hand facts. A stop by the cockpit before the walk-around inspection is critical. One must be certain that the important documents are on board and displayed properly. It is the direct responsibility of the owner to ensure that these documents are always in the airplane. The owner must display in the airplane at all times the airworthiness certificate, the aircraft registration, and the aircraft radio station license. The weight and balance information and, if alterations or repairs have created it, a Form 337 must also be on board. One should never fly without the pilot's operating handbook or, in the case of earlier model airplanes, placards displayed in the proper position. The handbook is your court of last resort, superseded only by service bulletins with a later date of publication. If you find any part of our tape to be in variance with the handbook, service bulletins, or the placards, they take precedence over our tape and should be followed. The aircraft and engine logbooks may be the best for record keeping, although complete records may be kept in another format. Records must always be made available on request. The results of the entire maintenance program should be entered, even the minor work performed by the pilot. Of particular importance is knowledge of the ADs, or airworthiness directives, which have been complied with on your airplane. A new owner may be horrified to find that his airplane is deficient in a number of very important directives if he has not made a thorough logbook inspection a part of the purchase process. The 172 has been remarkably free of airworthiness directives. However, it would be wise for aircraft owners to visit a local FBO and secure a list of ADs that apply to their airplane if they have not owned it since new and have followed through on every compliance. One should check these against entries in the logbook, and if the plane is deficient, bring it up to standard immediately. We will now look at the flight control system on this airplane and reinforce the information from tape 1. We are not interested particularly in the aerodynamics, but we are very interested in what can go wrong and what you, the pilot, can do to prevent problems by simple observation and early action. The control lock should be removed. The inclusion of this item on a checklist may seem unnecessary, but we can give chapter and verse of attempted takeoffs when the removal of the control lock had been overlooked. The check of flight controls is seldom performed in a thorough manner, in spite of the fact that malfunctioning in this area can leave us with a primitive form of an unguided missile. They must be locked and secured before we leave the airplane after a flight, and they should be thoroughly checked before a flight. The SDRs detail incidents of, quote, elevator flopping in wind after thunderstorm, unquote, and another, quote, elevator downstop bolt found bent and broken out of attaching nut plate, damage due to not using gust locks, very costly, unquote. These two incidents were not unique. They were taken at random. A number of owners paid dearly each year because of this moment of carelessness. In this check, we are interested in freedom of movement. The mechanical linkage, the cables, pulleys, and attach points all offer opportunities for failure. The routing on these cables is through areas of wiring and tubing which may impinge on the cables if they become loose. A likely wear point on cables will be at the cable area where they cross a pulley. Those that ride the pulley with no bend have a higher wear probability. A slow fingertip pull for each surface individually will let us find undue resistance. If we are in a quiet area, by listening carefully, we should hear any sound of metal scraping over metal if cables are no longer secure. We should conduct this check from time to time in a quiet place. Contrary to what you might have heard, it is a good idea to check the controls through full movement from time to time. It should be done slowly and gently, but firmly. Do not ever bang the controls against the stops. One of the SDRs justifying this check does grab your attention. Had the fellow in this airplane been a super brave type trying an aggressive entry and recovery in a spin, he could have had a hell of a surprise. Quote, "Controls hung up in full forward position. Stop bolt was installed in old hole, allowing stop to slip under bolt and hold controls forward." Unquote. Factor that one into the price of maintenance, sports fans. Move those controls through the full travel carefully with an understanding of what you are looking for. In our walk-around inspection of the elevator, behind the skin surface inspection, we are concerned about the same sounds and feel we worked with in the cockpit. But now, fittings, attach points, rivets at attach points, and brackets must be studied. Frayed cables, cracks in brackets and at attach points, as well as the security attachments themselves, must all be suspect. One of the things we will look for is play in the attaching points for the trim tab on the right-hand elevator. This is the actuator that is located in the back of the horizontal stabilizer on the right-hand side. The shaft moves back and forth as you turn the trim tab control up in the cockpit. When moving the shaft by hand, you will get a small amount of movement, but if the movement increases over time or is excessive, it should be referred to a qualified A&P. We cannot overstate the importance of the provisions for security in very critical items on the airplane. Attach points, hinge points where direction of motion is changed, and all the other points where a bolt or a unit of some kind must be secure are protected with the additional margin of safety provided by safety wire and cotter keys. Castellated nuts like the one shown here fulfill this function very well if they are equipped with cotter keys. When you see one not so equipped, you should find out why. In this area, aside from skin surface, we are interested in full freedom of movement of the controls and tabs, and proper response on input from the cockpit. It may be wise to have someone activate the controls while the pilot observes. Always be certain that trim tabs are returned to their proper position when this is done. The manufacturer has a published cable tension number which pilots and mechanics may find distasteful. Often we hear that the manufacturer's numbers do not provide the control feel that they desire, and the tension is changed, often as much as 30%. This may be operationally pleasing, but we suspect it would be indefensible in court. An owner pilot should know the manufacturer's recommendations and compare them to those on his airplane. This might offer an opportunity to experience flutter. An extreme case, hopefully, unlikely but possible. Small, slower-flying airplanes seldom encounter this phenomenon, but it is not unknown. It could be a product of unbalanced control surfaces and/or improper control response, which may be a product of corrosion. One may find a slight nibble, leading to a sudden and dramatic onset. At the first indication of this impending disaster, instant speed reduction is the best hope for recovery. Close the throttle, but handle the controls gently and quickly reduce the speed well below the flutter threshold. The aileron system is quite simple in design, but you will note that the cables run through several 90-degree bends en route to the surface itself, which makes the security of the pulleys very important. The cables also rise to the wing through an area very prone to corrosion. The aileron check follows the same procedure regarding feel and sound as the elevator check. We call your attention to the connecting chain and sprocket behind the instrument panel. If these become sufficiently worn and loose, all manner of unpleasant things could happen. The check on this is to hold one wheel firmly and rock the other one. If the play seems excessive, ask an expert. It may be a very important question. Other possibilities are equally entertaining. Consider this service difficulty report on a 172N. Quote, found aileron cable rubbing into fuel line in right rear door post area. Cable had rubbed through protective cover and slightly scored the fuel line. The fuel line support clamp had worked loose and the cable was improperly routed, allowing the cable to contact the line. Unquote. The ailerons are attached to the trailing edge of the wing by 3 piano wire type hinges on each aileron. This type of fastening was made famous by the aircraft industry of England in World War II. Hinges are secured to the trailing edge of the wing by screws and nuts. The hinge pin is secured by cotter keys in a track very carefully drilled to block the removal of the pin until the key is removed. We have seen reports that the drilling has been less than perfect in some cases, and the keys block nothing but air. AD 83-22-6 refers to this, but the problem has been found outside the serial numbers covered. Check it out and be certain that cotter keys are there and in place. Like other types of cable systems, these seem to invite intrusion by foreign objects, and this SDR reinforces our argument that a good control check is worthwhile. Quote, found aileron travel slightly stiff, found a retaining button used to hold control shroud jammed between cable and pulley. Unquote. A prudent person keeps buttons buttoned. The attention given to the rudder on the airplane by many pilots seems to be confined to wiggling them a bit on the control check and wondering why it seems to be so hard to keep the ball in the center in flight. The very simplicity of the system seems to cause us to frequently dismiss it as being trouble-free. The rudder pedals are straightforward and apparently would do justice to a 747. In conjunction with the brakes and a little help at the nose wheel, they steer the airplane on the ground. We submit the following SDRs for your consideration. Quote, pilot reports aircraft required more left rudder than usual. Rudder torque tube bearings attached to aircraft structure are pulling out of floor and support structure. Unquote. And, quote, during a 100-hour inspection, it was noted that the rudder pedals on the left side were loose. After removing the rudders, it was found that the pivot shaft holes were worn. Submitter recommends a very close inspection of the rudders on the left side. Unquote. Much of the rudder mechanism is visible to the pilot on a walk-around inspection, using the same standards applied to the other movable surfaces. We suggest that, as you leave the cabin for the pre-flight, you apply side force on the pedals and rock the pedals back and forth with your hand. Note the relative simplicity of the rudder movement. You may move it with your hand and see several important points which are readily visible. As with all the surfaces, the attach points and the rivets supporting them to the structure and as far into the leading edge area as you can see must be monitored for security and corrosion. What is perhaps the most important is not easy to see. There have been many reports of corrosion and rust damage to elevator and rudder cables in the fuselage. The most common cause of this problem is birds' nests. A flashlight, a little agility, and eyesight on the order of 20/20 should expose the little rascals in time if you worry about it in time. Getting them out may be another matter. Your friendly fireman won't do it. you may need an A&P to do a little disassembly. You are looking at the rudder trim tab. The flexible tab on this model is designed to overcome an out-of-trim condition noted when you are unable to keep the ball in the turn coordinator centered in straight and level flight. It was introduced in 1969 on the K model. Have adjustments on this tab done by someone who is qualified to do this sort of thing. In 1977, an optional rudder trim mounted on the pedestal was offered on the N model. This enabled the pilot to trim in flight and is much more satisfactory. The importance of trim and rigging has not been properly appreciated by many pilots. As we shall see in the section on the fuel system, improper trim is one of the causes of uneven fuel feed. A rather simple check on aileron rigging is a carefully controlled straight-ahead stall. If the brake is straight with little wing-down movement, trim is probably all right. If the airplane tries to fly with one wing low or in a yaw, a very likely cause will be found in the tie-in cable between the rudder system and the nose wheel. The tension is probably wrong. Many mechanics have been known to bend the rudder tab to correct this condition. Generally, the results are not impressive. A fact that is often not considered is the effect trim and rigging may have on performance. There are several STCs which offer increased speed, but if your budget and inclination do not lead you in that direction, a few hours invested in rigging and trim may make you happy with some increased performance. If uneven fuel feed has been a problem, you will probably gain improvement in that area as a bonus. The fittings which control surface movement are particularly important and should be looked at very carefully. Beyond this, the cable system which transfers the pilot's input to the surfaces should be a matter of concern. If we go into a careful and thorough pre-flight and walk around inspection, we will be able to get a handle on the maintenance standard that has been applied to the airplane. The pre-flight inspection is often treated carelessly. Aside from the safety items which may be uncovered, a pilot performing preventive maintenance will need to constantly monitor the well-being of the airplane. The fact that a pilot is empowered to remove the cowling and inspection plates, provided they are replaced to the satisfaction of an A&P, is a long step forward. We have covered much of what the pilot should see in tape 1 of this series. The exterior walk-around inspection should be used to reinforce the information you have gained in the cockpit. You should touch and activate the same controls you activate in the cockpit. Items that may seem obscure should be examined for possible decisions. Cessna suggests that this door be locked if a child's seat is installed. We suggest that it should always be locked in flight. Unfortunately, the lock did not become available until the 1973 model. All skin surfaces are worthy of close inspection, but it is particularly important on empennage surfaces, including the horizontal and vertical stabilizer. The firewall area is particularly susceptible to cracking and wrinkles if hard landings or nose wheel first landings have been made. If cracks, wrinkles, or corrosion are found, they must be examined in depth immediately by a qualified repair person, and complete findings be made a matter of permanent record. Court cases have been entered where wrinkles over 20 years old were part of the basis for a decision. Aside from taking you to court, these imperfections can lead to tragedy if they are not handled in a timely manner. In passing, it is worth looking at the tie-down ring. We once witnessed an attempted takeoff in a tiny wooden airplane with a large concrete tie-down block firmly anchored to the tail wheel. The little plane flew a little, but the block was never able to get airborne, although it did bounce rather well. Finally, the tiny craft reverted to its natural state of kindling wood. The pilot said he thought it taxied funny. The media thought it was funny too. We now direct your attention to the flaps. From time to time, the walk-around inspection should be done with the flaps in the full down position to evaluate the condition at the attached points. There is some variety of methods of lowering flaps, but this model works with an electric motor protected by a 15-amp circuit breaker. If the circuit breaker pops out, and pops out again when it is reset, the landing should be made with no flaps, with no more attempts to reset the breaker. This airplane has a single slotted flap, which is designed to droop below the trailing edge as much as 40 degrees in some models when fully lowered. The flap section is pushed back and away from the wing as it comes down. This allows high-energy air from below the wing to be ducted over the flap. The renewed airstream gives the boundary layer needed velocity to delay airflow separation, which increases the coefficient of lift further. With the flaps in the full flap position, this will give a reduction of stall speed of 8 to 11 knots. It is well to be aware that a go-around from the flaps full-down configuration, one should accelerate before retraction, keeping in mind that there is a reduction in aircraft strength with the flaps extended, and VFE should not be exceeded. Prior to 1972, owners were advised to handle flap settings with caution in side slips. An upwash increment from the upturned aileron created a downwash angle over the horizontal tail. The resulting nose-down pitch often created enough negative G's to throw the pilot forward against his seatbelt. This phenomenon was not consistent, but very experienced Cessna pilots have suggested that 20 degrees for crosswind landings should be the maximum. The extended dorsal fin has largely canceled out this problem. Intergranular corrosion on the flap tracks and wear on the rollers has been a problem, and careful inspections should be made with the flaps extended from time to time. The tracks should be clean and free of grease. They may be washed with Stoddard solvent. This is something every pilot should be aware of. Black stains in an area of the surface where there is not likely to be oil stains are very likely powdered aluminum. This indicates wearing abrasion of a serious nature. Rivet heads may be the first casualty, but any point of surface-to-surface contact should be suspect. This may indicate improper rigging and/or a malfunctioning limit switch. An inspection of the leading and trailing edges and wingtips is important for other reasons as well as safety. If you find hanger rash in time, you may also find someone willing to pay for having it fixed. Careful attention to the wing is particularly important in older airplanes. As we have noted, we have seen recent service difficulty reports spelling out spar cap corrosion. Look as carefully as you can in your inspections, and discuss this with your A&P when convenient, particularly if the airplane has been operated in a high-risk area of high humidity and/or salt. Inspection of the landing gear area should range from the attach points at the fuselage, where the interest may include possible wrinkles indicating hard landings, and extend to the brakes. It is somewhat difficult to evaluate the brakes on these airplanes with the wheel pants installed, but cockpit indications will tell us much. This pitot static system drives the readings on the airspeed, the altimeter, and the rate of climb indicator. The pitot tube provides the ram air source, and there is a static port on the lower left nose section. Your pitot head may have a heating element. If so, check it from time to time by turning the heat on briefly and touching it gently. You should also get an ammeter indication when it is turned on. Most instrument pilots turn the heat on anytime visible moisture is expected. Do not blow into this pitot head. Contrary to popular belief, ice blockage in the pitot head may not reduce the airspeed reading to 0. If the pitot head is frozen, only static air will be driving the airspeed. From an NTSB report, we find that an airline captain on a ferry flight failed to follow his checklist and turn on the pitot heat. As he climbed, the airspeed apparently increased. To compensate for the supposed buildup, he pulled the nose up until he stalled and spun in. When instruments appear to fail in this system, Pulling the alternate static air valve will move the source from the static port to the cabin interior. This will create a modest variation in readings, which should be noted, but if the pitot head is iced up, it will not restore the proper airspeed reading. The tape covers used on the airplane static system during washing should always be removed before flight. The brain of the engine is the ignition system. This consists of several elements. The ignition switch has an off, left, right, both, and start position. The dual magnetos are manufactured by either Bendix or Slick. Spark plugs of a specific type are spelled out in the owner's manual or the maintenance manual. Other than the battery for turning the starter, the ignition system is independent of other aircraft systems and is activated when the engine is turned over either by the starter or manual movement of the prop. The magnetos fire independently, and if they are not grounded and are hot, they will fire with a rotational movement of the prop. Thus, people around a propeller should always treat it as though the mags were hot. There is no guarantee that the off position which grounds both mags through the P leads is functional. A simple check of this problem is to very briefly turn off both mags from a low idle condition of 500 or 600 RPMs. A moment of silence will tell you that the mags are grounded when the switch is off. Do not use a higher RPM, which might cause a backfire. This check will not give you carte blanche to be careless around the propeller. A P lead can malfunction while you are getting out of the airplane. The left mags fire the top plugs on the left side of the cylinders and the bottom plugs on the right side, with the right mag firing bottom on the left and right on the top. The both position allows a sequential firing order of both. When the start position is selected, it permits power to flow to the starter from the aircraft battery. A sliding mechanism on the starter will then move forward and engage the teeth of the ring gear, which will cause crankshaft rotation. The magnetos fire, and, if the other necessary things have been done, the engine will start. As the engine fires, the pilot will release the start position to both, which downpowers the locking mechanism on the starter. With the power off the unit, the spring-loaded locking mechanism will be pulled back to clear the ring gear, and the starter will remain inactive until called upon again by the pilot. Hopefully. Now, what could go wrong with a simple system like that might cost a great deal of money and leave the pilot's neck on a chopping block? According to the SDRs, quite a number of things. I quote, "Ignition switch failed to return the switch from start to both. The aircraft departed with the starter still spinning. When the starter overheated, it drew more and more current, which damaged the starter contactor and the voltage regulator. Once the voltage regulator failed, the battery quickly failed and began to smoke." Unquote. An occasional thing, you say. No, not really. Let's look at this one. Quote, "Pilot experienced total electrical failure 6 minutes after departure. Returned to field, ran off runway, struck prop on obstruction. Found starter motor burned up. Start contactor point burned and pitted. Submitter suspects contactor stuck, causing starter to remain engaged, burning up starter." Unquote. What can I do in a situation like that, you might ask? It's easy. Don't get in a situation like that. You have procedural tools to avoid it in most cases. Learn to religiously check your ammeter, an instrument we will talk a lot about later, and if it doesn't show a return to a normal charging rate very soon after the start, shut the engine down and find out what is going on under the cowling. If the charge rate is still excessive at takeoff time, and if as much as 5 minutes has elapsed, be very suspicious. A couple more things about the ignition switch. One pilot found that when his engine quit with sudden dead silence at altitude, that wiggling the ignition switch restored power. It's worth a try if it happens to you, but we suggest that if the switch can be wiggled around very much, you probably need a new switch before you do much flying. Another person found that the key could be easily pulled out of the switch when it was in the both position might not be a bad thing to check the next time you pre-flight. Mag timing should be checked every 100 hours by a competent mechanic. An indication of this problem for the pilot's attention might be engine firing backward, jerking the prop back momentarily in the starting process. If the engine starts after the release of the starter, it is probably an impulse coupling problem. Be very prompt to seek knowledgeable help when mag symptoms develop. The mag may destroy an engine if it comes apart. A specific magneto check is mandated by an AD for Bendix mags, and Slick recommends a complete check at 500 hours. Beyond this, the magnetos are sealed units and not likely to be examined by the pilot beyond the routine left both, right both ground check. But this check, usually performed between 17 and 1800 RPM, tells us quite a bit. The magnitude of the individual drop is not as important as the difference in drop from right to left. This difference should not exceed 50 RPM. If it does, the problem very likely will be in the spark plugs, and in most cases can be corrected by leaning the mixture and applying a few seconds of fairly high power. If the problem was fouled spark plugs caused by idling at a very low RPM, that should clear the problem. If it does not, a mechanic may want to pull the plugs. You, as a pilot, are permitted to do this provided you know and understand the procedure and have a qualified mechanic to back you up. Contrary to what you might think, this is an intense procedure filled with pitfalls and must be done correctly or major problems might develop. A non-electrical potential problem in the starting sequence is the management of the prime. Cessna details use of the primer in the start procedure, and we feel 1 to 3 shots, depending on temperature, will be adequate. The electrical system on this airplane is a 14-volt, single-wire, ground return system. This means that power distribution to most units is through a bus bar, and each unit is grounded to the airframe. The bus supplies a circuit breaker panel with each breaker clearly identified as to purpose and amperage. In 1978, the 14-volt system was changed to 28 volts, beginning with the 172N. But the principles below are not radically different. The power sources are a 14 or 17 amp-hour battery and a 60 amp alternator. Earlier models had generators, but all can be converted. The alternator produces AC current, which is converted to DC by a silicone diode rectifier. This DC current resupplies the battery and is directed to the main bus through a 60 amp circuit breaker. The main bus is the primary distribution path for aircraft power requirements. The electrical energy powers the starter, the lights, the avionics, the flaps, some instruments and switches, and the pitot heater. A communications center to the pilot is found in the ammeter. This indicates the charging rate to the battery, and the information tells the pilot a great deal about what is happening in the electrical system. Most electrical problems relate to insufficient rate of charge or to excessive rate of charge. The master switch is a split rocker type switch with on and off positions beginning with the 1970 172K. The left half, labeled Alt, controls the alternator, and the right half, labeled BAT, controls all electrical power to the airplane. Alt Off will drop the alternator from the system, leaving only the battery to handle all loads. The battery is used for normal starting, absorbing system surges or spikes, and for emergency electrical power in the event an alternator failure should occur. The battery box, in use until the N model in 1979, is vented overboard to dispose of the electrolyte and hydrogen gas fumes that are discharged during normal operations. To be sure these fumes are disposed of properly, it is a good idea to frequently check the vent hose connections at the battery box for obstructions. A major source of dangerous and expensive aircraft corrosion may be found in this area and is always the product of neglect. One SDR reported that the battery box had come completely detached from the firewall and fell into the cowling below. The electrolyte level in the battery should be checked every 25 hours of operations. The level should be maintained by adding distilled water only. Add only enough water to cover the plates and never fill more than 1/4 inch over the separator tops. We suggest at this time that the battery be removed and the battery and box be washed with a soda water solution. Normal operations may not require much service. However, hot weather operations may dictate more frequent checks. The battery check is seldom done by most owners, but it is a very inexpensive way to head off costly repairs and possible replacement due to a low, dead, or frozen battery. Remember that a low battery can freeze as high as 13 degrees Fahrenheit, whereas a fully charged battery will still be reliable to nearly -80 degrees Fahrenheit. The owner is entitled to perform battery maintenance under certain prescribed conditions, and this is one area where many savings can result. Like most things on an airplane, mistakes can be costly, and one should learn the proper maintenance techniques. Provisions have been made in the construction of the aircraft to make it possible to have a fully discharged battery in the aircraft during an APU start. This approach should be treated with caution. The battery could accept a high rate of charge over a long time period, and this could overheat the battery. This could boil out the water, or it could buckle the lead plates and eventually damage the battery beyond repair. It would be better to remove the battery and have a bench charger hooked up. This way, the battery can be charged at a lower rate and the battery condition monitored during the recovery period. A normal battery will require only a trickle charge to maintain its full charge condition. During an engine start, there will be a large drain on the battery. With the alternator on the line, there will be a high charge rate that will gradually diminish until the battery is fully charged. It may take 5 to 10 minutes to complete this charge cycle if the battery condition was low to start with. The 172 does not make heavy demands on the battery in normal operations. Thus, an extended high charge rate may be an indicator of trouble and should be regarded with suspicion until the cause is known. A battery that has a dead cell or shorted plates will continue to demand a charge. This can be detected on the ammeter if there is indeed a short. The battery check will continue to show a higher charge rate as long as the battery is in the system. The battery can be isolated by turning off the battery master switch. When the battery switch activates the primary bus, it leaves the avionics bus in a standby position, and it will be powered only when the avionics switch is turned on. Although the primary bus is not affected by the use of a power cart or the demands of the starter on the battery, much care must be given to ensure that the avionics master is off when these power surges are employed. A great deal of damage to the avionics gear is possible when this is ignored. The avionics switch should be on only when you are assured that there will be no transient voltage spikes. Although it is protected by a circuit breaker switch, the best protection is isolation. When doing ground service on the avionics equipment, it is recommended that a battery cart be employed to ensure a stable power source. Charged completely, there will be no hope of regaining power from the alternator, even if it was operating at the time of shutdown. The alternator requires at least 2 amps to the field coil to excite and begin operation. Upon shutdown, it retains very little residual magnetism and must have the battery to provide the 2 amps to the field circuit once again. With a ground power unit plugged in, a special fused circuit will close the contactor when the master switch is turned on. This will allow a dead battery remaining in the aircraft to take a charge and activate the alternator when the engine is started, although this, as we have stated, should be handled carefully. A voltage regulator, operating on a demand basis, controls the voltage output. If the voltage is too high, a movable contact puts a resistor in the circuit. This drops the excitation and the output voltage. If bus voltage is too low, the coil spring removes the resistor and increases output voltage. By the time the flight has stabilized for a time at altitude, the ammeter indication should be less than, certainly no more than, a 2-needle width charge rate. If it exceeds this indication for an extended time, the battery may overheat and boil away electrolyte. If a faulty voltage regulator is the cause, electronic components could be damaged. When the rate reaches a preset value, the overvoltage sensor will shut down the alternator and light the overvoltage warning light. This light is not always located in a highly visible area, and it is often difficult to determine if it is indeed lighted in certain lighting conditions. If in doubt, cup your hand around the light to darken the area. One may check to determine if the problem was a transient one by turning off the avionics master switch and then turning off the alt and bat master switch. Turn the alt and battery switches back on. If the warning light does not come back on, normal charging has resumed and the avionics master may be turned on. If the light comes on again, a malfunction has occurred and one should go immediately to the electrical malfunction checklist. Land as soon as it is practical to do so. Conserve electrical energy. A continued discharge rate indicates that the alternator is no longer producing power and should be shut down. Shed non-essential electrical loads and land as soon as possible. An owner who is interested in preventive maintenance would do well to examine the state of the alternator on pre-flight. Loose or broken belts or cracks near the welds might be uncovered before they become a major problem. We refer you to a few things our research has turned up. Quote, shortly after takeoff, aircraft experienced alternator failure. Investigation of cause revealed alternator belt had been broken by the alternator's upper support bracket coming loose, falling out, and becoming wedged between the engine drive pulley and belt. Unquote. Shake those things and pull on the belt at pre-flight. Look as far as you can see, and when you have time to get the cowling off, get a little mirror and flashlight and look the area over. Here is one that says something about carelessness. Quote, upon removal of the cowling for oil change, it was noted that there was an oil leak. During inspection for the oil leak, it was found that the wire bundle for the alternator and the starter wire were improperly secured to the oil return tubes, causing the wires to chafe the tubes and eventually cut them. Unquote. We won't quote the price of an alternator, but we are told that a large number are replaced each year simply because the maintenance people failed to do what these people did to solve the following problem. Quote, intermittent loss of alternator field voltage, cleaned terminals and switch, problem solved. Unquote. Before you buy an expensive alternator, put a meter throughout the system. An ammeter needle flickering may be the first indication of corroded terminals, which would create resistance in the circuits. Voltage readings taken at the alternator output with engine running, at the bus bar, at the voltage regulator, this line is usually orange, and at the overvoltage relay. For example, an alternator reading of 14.5 with the voltage regulator sensing 13.5 volts would indicate resistance in the circuits. By the time the problem has progressed to the point of complete loss of field voltage, many owners are quite receptive to owning a new alternator which will last about 4 months. A little time in cleaning the terminals may save you enough money to fly down to Acapulco. Let's look at an unethical and dangerous practice. The SDR reads, quote, alternator inoperative, found auto brushes installed. Wire in one brush came unbonded. Brushes worn out at 241 hours total time. This alternator overhauled by repair station. Submitter states auto brush leads copper colored, aircraft brush leads silver color. Keep finding this in overhauled alternators, unquote. If I did this, with my luck, I would probably land in jail. And so it goes. Loose inspection of the leads, the belts, the pulleys, the brackets, the switches, all leading to failure, forced landings, some pain and suffering, and nearly always a deflated wallet. This tape just isn't long enough. There are enough examples to fill a library. Just about the worst encounter you may ever have with your electrical system would be an electrical fire in flight. Although this seldom leads to tragedy, it is guaranteed to grab your attention. If you have been paying close attention to the ammeter, the incident may not be totally unexpected. You will certainly have a very significant increase in charge rate as something in the system begins to heat up. If you have been enjoying the scenery too much, probably the first indication will be the smell of burning insulation. If you are not familiar with this smell, it is a sweet smell as compared to the oil and gas fire smell. This will be followed by wisps of smoke, but don't wait for them. At the first indication, grab the proper checklist and go to work. Follow it step by step, very carefully. If you delay, that little bit of smoke can begin to billow, at which point you may have a very bad day indeed. In the event of an electrical fire in the aircraft, it is necessary to remove all of the power from the electrical system. This can be done quickly, simply by turning the battery and alternator switches off. Once this has been accomplished, we can turn off the rest of the individual electrical components. Then, with the battery and the alternator switches back on, we can rebuild the electrical system by individually turning on essential equipment while noting the ammeter indication. The faulty equipment can be detected by an excessively high draw when that component is turned on. Turn it off, pull the appropriate circuit breaker, and leave the component without power until inspected and repaired. Internal propeller failures are generally not within the control of the pilot. However, subsequent actions are, and the wrong response can have dramatic results indeed. Procedures which might avoid failure and blade care are under pilot control. Both must be correct and stem from knowledge, or your engine may begin to sound like an electric motor just before it leaves the plane. We are sure that the pilot of this 172M could give a much more dramatic account of the importance of this mindset than the simple line in the accident report. Quote, 18 inches of the propeller blade separated in flight, unquote. We do not know how the pilot handled this failure, but it seems to us that should one seem imminent, the best chance is immediate closing of the throttle. If you are successful, the vibration will no doubt discourage you from opening it again. We need not experience the airborne equivalent of being struck in the head with a 2x4 to know that the blades deserve close observation during pre-flight for nicks, stress cracks, or abrasion. Any type of damage exceeding 1/8 of an inch in depth should be referred to a certified mechanic for repair. Nicks in the outer 18 inches of the prop blade must always be treated as critical. This is the area of highest vibratory stress, and all repairs must be also accomplished parallel to blade axis. Do not attempt to perform any minor maintenance on the prop unless you hold the proper license. Remember, these blades must carry a centrifugal load at full RPM of many tons. Also, anytime the surface of the prop is abraded in any way, the corrosion protection is lost, and that prop should be retreated. The spinner bulkhead is prone to cracks and should be examined, and the crankshaft seal should be checked for leaks. Now the tach. If readings seem to be going astray, the tachometer should be recalibrated. A 10% variance may call for a replacement. Your first indication of this problem could be a noticeable difference between the cockpit indication and the actual performance, or an inadequate or excessive reading on a power check. If you suspect this problem, act on it immediately. If loose gravel or small stones are present in the takeoff area, and if room permits, the throttle should be opened slowly until the airplane is rolling fast enough to blow stones to the rear rather than up into the prop. We suggest that an area like the one shown here should be avoided like poison. To your propeller, it is cyanide. One more thought on the prop. Avoid turning it backwards as much as possible. The vacuum pump hates it when you do. As a pilot, you are not charged with a requirement to understand the inner workings of your engine in fine detail, but you should know enough to practice correct operating procedures if you are not going to make an unscheduled call on a farmer below. Let's look at what makes the power plant go. Obviously, it is fuel and air, with the oil system helping. The system consists of 2 fuel tanks, which by virtue of the high wing design permit a gravity feed to the strainer and carburetor. In spite of the simplicity, the system is responsible for a high percentage of SDRs on the airplane. A check of the fuel quantity gauges is necessary as a cross-check of your visual inspection at the filler points. Note the readings and compare for accuracy. Fuel mismanagement can lead to one of the most embarrassing and potentially dangerous episodes in a pilot's career. One should always begin a pre-flight analysis of fuel requirements with a healthy skepticism of the fuel gauges, the published fuel burn numbers of the manufacturer, the winds aloft, and FAA's published minimum fuel requirements. Each aircraft should have a fuel burn log, and the pilot in command should trust no one but himself in determining that the fuel requirements for each flight are met. Nor should a pilot hesitate to land and top tanks away from home if the plan begins to go astray. A pilot may be complacent about the stock market or a poker hand, but the stakes are much higher when one becomes complacent about fuel requirements. As you shall see, the airplane has enough problems with fuel without the pilot adding to them. The fuel flows through a 4-position selector valve labeled left, right, both, and off. In the both position, the 2 tanks are fully interconnected, and fuel may flow from one tank to the other. This makes it impractical to measure the fuel burn in any one tank, but rather requires that fuel burn be taken as a total. Care must be taken when the aircraft is parked that the fuel valve is either in the left or right position. Otherwise, if the terrain places one wing higher than the other, fuel may be vented overboard. Of greater importance is the fact that condensed moisture may run away from the sump drains and not appear when the check is made, but will return to haunt you when the plane is in level flight. There has been a continuing complaint about uneven fuel feed, and the left and right selectors are used to level tanks and avoid wing heaviness. Vapor lock has also been a problem, and some placards have been issued requiring a switch to single tank operation above 5,000 feet. In the event of engine stoppage, switching tanks immediately to a single tank, not both, and then back, has been successful in restoring power. The interconnected vent system is also critical. The right filler cap and a vent located under the left wing in the stagnation region behind the strut provides stabilized air for the system. This position minimizes ice blockage. The left wing vent vents overboard, but functions as a check valve. This vent has a history of becoming plugged. It seems to attract insects. The positioning is important, since some movement might place it into a ram airstream or into a position to get a venturi effect, applying either pressure or suction. The check valve will continue its protective function, but the vent system will be inoperative. Both of these vents should be examined with great care to determine that they are functional. It has been suggested that air pressure applied by blowing through a surgical tube fitted over the vent can determine if it is clear. If a blockage is encountered, someone familiar with the procedure may blow it clear with compressed air after removing the filler caps. It is important that this vent not be confused with the pitot tube when this check is made. Beyond this, flying the airplane with the ball out of center may promote uneven fuel feed. A recurring problem that is important is cracking at the welds around the filler port. The refuelers lean the nozzle against the side of the opening, and it is not stressed for this. The pilot should confirm that the refueler is aware of this and will conform to the proper method before he entrusts the fueling to him. A typical report reads, quote, "Pilot reported fuel leaking from bottom of wing. Inspection revealed that the fuel tank was cracked around the fuel filler bracket adjacent to the weld, probably caused by fuel nozzle resting on filler bracket when servicing. Tank leaked only when full with fuel." Unquote. In this case, there may be a strong fuel smell in the cockpit when the tanks are full. First and foremost, we want to determine that there is no water or other impurities in the fuel. We know failure to make this simple check created an unscheduled landing in the middle of an African jungle for the writer of this segment. The color and smell identify the grade that is specific to your engine. Refuelers have gone so far astray as to load jet fuel in reciprocating engine aircraft. This check should be done at all drain points, but is particularly important at the strainer drain. It is possible to obtain an STC to use automobile gas. Quote, "Aircraft is certificated to use auto fuel. Used it for 2 to 3 years until found under certain conditions it would get vapor lock if it were flown on a hot day. If parked for a few minutes, then started and a takeoff attempted, it may lose power abruptly, gets your attention, and could be disastrous." Unquote. No comment, except one fellow who was using auto gas found his sediment bowl full of sand. If you are using it, be sure of the quality control of your supplier. The fuel and air meet in the carburetor where they are mixed in the proper proportions. The throttle and the mixture control adjusts the air and fuel being fed through the induction system. The mixture is taken into the cylinders through intake tubes, leading to intake valves, and introduced to the combustion process by the firing spark plugs. The exhaust valves open, and exhaust gases perform other functions en route to going overboard through the exhaust tubes, the muffler, and the tailpipe. In your inspection of this system, you will be interested in cracks around the welds where the exhaust tube joins the cylinder. Unequal expansion makes this area a likely spot for cracking. The exhaust gases going through the muffler provide a great deal of temperature to the muff surrounding the muffler, which can be used to warm the cabin. A most important function for the pilot is the measurement of the exhaust gas temperature through a probe located high up on an exhaust tube. This information is read out on the EGT gauge in the cockpit and is the primary tool for the efficient management of engine operation. As might be expected, the carburetor is more sensitive to careless inspection than most other systems. It receives errors from the induction system as well as the fuel system. For example, quote, "Pilot reported engine failure 100 AGL after takeoff. Safe landing made on remaining runway. Paper element from filter found shredded and injected into carburetor." Unquote. Quote, "Excessive buildup of birds' nests in the engine compartment. Debris somehow worked its way down through hoses into carburetor intake, blocking venturi, not allowing static RPM for takeoff." Unquote. Even if you use intake plugs, leaving your aircraft parked for some time with the prop in a vertical position may not be a bad idea. Or from an accident report, quote, "After aircraft had forced landing, FAA wanted to run engine. On preparing to run engine, noticed water in sediment bowl. Fuel line had separated from carburetor during accident. When fuel shutoff valve was activated, water came from left tank. When checking quick drain, no water present." Unquote. Drain them all, folks. As if the poor carburetor didn't have enough troubles from outside, it has some of its own. The float occasionally fills with fluid. Probably the best chance the pilot has to find out about this is when the engine quits in climb or descent. It may run okay for a while in level flight. If this happens, you can probably work out the descent all right, but there will be no more climbing for the day. Another very good indication of this trouble will be the engine operating erratically or dying in low idle or on rollout. The carburetor air box channels air to the carburetor, and provisions are made for cleaning and warming the air as necessary. First, it must pass through the air filter. The filter consists of a retaining mount in front, followed by a paper or foam filter, and then a wire mesh to hold it in place. The filter should be checked for foreign objects and cleanliness, but the filter itself may present a hazard, as SDRs attest. Quote, "Expanded mesh came apart in 4 pieces, allowing foam filter to be ingested." Unquote. This is not a one-time thing. In addition to foam, in others, paper and wire worked their way up to the carburetor. From the filter, the airflow goes to the air box, then to the carburetor, and to the intake tubes, on its way to the cylinders, where it performs its mission. If ice or debris should block the flow of air, and there was no alternate source, the engine would surely die. Fortunately, there is an alternate source. Unfiltered air is obtained from the engine compartment to a shroud around an exhaust riser which heats it. From there, it flows into the air box. The amount of heat is regulated by the carburetor heat control on the instrument panel. The control operates a valve in the air box, with the valve setting determining the amount of heat flowing to the carburetor. 2 properties of this unfiltered air are changed. 1, since the air comes from the engine compartment, ram effect is lost. 2, the heat makes the air less dense, so we may expect a reduction in power and a consequent mixture enrichment. This may be reflected in the loss of as much as 225 RPM. The carburetor heat box has been responsible for the creation of several SDRs. This one is so similar to many others, it makes one think that some attention should be applied to this area. Quote, "During annual inspection, carburetor heat box valve shaft had loose rivets and was not giving full carburetor heat." Unquote. One thing is certain, on a carbureted engine there will come a time when you will want all the heat you can get, plus some more you will wish for. Carburetor ice formation is a hazard which may creep up unnoticed at first. The usual gradual power loss may be ignored or discounted at the pilot's risk, and attempts for correction may be made by simply advancing the throttle. If the condition persists, the engine will begin to run rough. Beyond this point, if indifferent or careless attempts to correct the problem are attempted, the engine may quit. Should this happen, the problem has taken on different proportions. The source of heat, a running engine, has been lost. When the symptoms appear, use full throttle and full heat until the engine is running smoothly. If continued heat is necessary, determine the control setting for minimum heat needed and lean the mixture as necessary. Throttle settings may be consistent with cruise operations. Quote, "Caution, carburetor heat should not be used during takeoff unless it is absolutely necessary for smooth engine operation and acceleration," unquote. This caution note from the pilot's operating handbook is a roundabout way of saying that you need all the power you can get for takeoff. And unless the power check gives you the required readings at full rich and full power, you might be able to cure the problem with carburetor heat. Treat this with caution. You may, in fact, in certain ambient conditions, raise the temperature in the carburetor throat into the icing range with a partial heat application. If you need carburetor heat to save yourself, lay into it with all there is and fine-tune it later. If your power check goes astray, find out why for sure before you open those throttles for takeoff. The takeoff run is no place to be analyzing a potential problem. As they say, if you see, smell, feel, or hear something going astray, close the throttle and find out what got your attention while still on the ground. It's better to be on the ground wishing you were up there than up there wishing you were on the ground. From the pilot's point of view, the control of the air-fuel ratio is probably the most important contributing factor to long engine life. Improper use of the mixture control can drastically shorten engine life and cause costly repairs. For this reason, we will turn our discussion to what is considered to be the ideal mixture and the problems associated with misuse of the mixture control. As we plot a continuous range of fuel-to-air ratios, at some point we will produce a mixture which develops the maximum amount of heat during the combustion process. This ratio is approximately 15 pounds of air per pound of fuel, or about 6 2/3%. The exhaust gas temperature gauge gives us a reading of this interaction and provides us with our best tool for proper management of our fuel and induction system. If it is used properly in the leaning process, it will certainly extend engine life. Properly, one should lean until the EGT peaks. Then the mixture should be very carefully enriched to the point that the excess fuel drops the temperature 25 to 100 degrees. Many pilots still prefer to lean to a slight roughness and then enrichen to smooth out. The argument being that uneven fuel distribution in the cylinders in carbureted engines might make for too wide a temperature variance cylinder to cylinder. If the EGT process leaves some roughness, this is probably so on your airplane, and you should continue the process to remove it. As we lean the mixture past the peak temperature, excess air will act as a cooling medium, and the normal temperature inside the cylinder will begin to drop. As we enrich the mixture above 6 2/3%, excess fuel will act as a cooling medium, and the temperature will again begin to drop. Best power is obtained at a slightly richer mixture than 15 to 1. Best power results when airspeed is maximized per pound of fuel burned. This is accomplished by allowing some of the fuel to go unburned and provide a slightly denser mixture in the cylinder. These unburned fuel droplets also carry off a lot of heat. Most engines do not require leaning below 5,000 feet MSL, and we may expect to hold our full rich takeoff mixture setting to that altitude, although Cessna calls for 3,000 feet in some cases. We may expect to lose about 3% of our rated power for each 1,000 feet we climb, and the mixture will enrichen as the air becomes less dense. In all cases, the pilot should follow the procedures outlined in the pilot's operating manual or in the displayed placards. Excessive leaning can lead to detonation and high temperatures and/or pre-ignition, or you could actually starve the engine of fuel by operating too lean. With an excessively rich mixture, you would have problems with high fuel consumption, ignition fouling, or loss of power and engine roughness. In a normal burning sequence, The ignition of the air-fuel mixture in the cylinder is actually a burning of the fuel, or what the chemist refers to as a flame propagation. It is not an instantaneous explosion. In an instantaneous explosion, the entire energy which is stored within the cylinder is released in an extremely short period of time. This is what is referred to as detonation. This closely approximates an explosion within the cylinder, as opposed to normal flame propagation. Instead of the piston being pushed down, it receives a hammer-like blow as the combustion forces are released virtually instantaneously within the cylinder. In its initial stages, detonation sounds are masked by normal engine sound or prop sound. The only indications will be a slight loss of power and abnormally high temperatures. When detonation has progressed to the point of recognizable engine roughness or knock, you may be only moments away from a complete engine failure. For these reasons, it is important to avoid the conditions which will eventually lead to detonation. Most of the principal causes of detonation are either directly or indirectly controllable by the pilot. Mixture must be monitored carefully at all times. The mixture will enrichen as you climb and lean as you descend, unless you make the appropriate adjustments in the normally aspirated engine. Another major problem that needs to be addressed is pre-ignition, the uncontrollable firing of the mixture before the normal spark ignition point. Pre-ignition can lead to excessive pressure within the engine. Some of the principal causes of pre-ignition are glowing spark plug electrodes, valve faces or edges which have been heated to incandescence, or possibly carbon or lead particles glowing within the cylinder. Another aspect worth mentioning is the effect that density altitude has on the normally aspirated engine under takeoff conditions. Using the general rule of thumb, we would again note that the loss of 1 inch of manifold pressure for those aircraft so equipped is equal to 1,000 feet above sea level density altitude, or about 3% of rated power. This may require proper leaning for takeoff. At Denver, with a field elevation of 5,333 feet, a 90-degree Fahrenheit day, and a 5,500-foot pressure altitude, our aircraft would feel as though it were roughly at an 8,800-foot density altitude. This is going to grossly affect our takeoff performance. How might we go about handling this high ambient condition? After engine start and during taxi phase, we might experience engine roughness while at idle RPM of 1,000 to 1,200 RPM. If this is the case, we would like to lean the mixture to smooth out any engine roughness that we are experiencing while we taxi. Just prior to takeoff, or possibly into position on the runway, we are going to make a very brief full power run up and are going to manually lean back using the EGT or simply removing engine roughness to establish the proper setting. Then we can continue our takeoff roll and rest assured that we have done just about all that can be done to develop the maximum amount of power that is available under these specific conditions. Thus, as we make our power check early in the takeoff roll, we can cross-check our RPM, EGT, and the manifold pressure if available, and ensure that they are within the parameters we have predetermined during our pre-flight planning. This will also tell us if we have proper power output to continue the takeoff. If we are uncomfortable with any of the readings, we should abort immediately within a safe stopping distance and return to correct the problem. This mindset, however, requires that we cross-check early and decide early. During a typical flight, after climbing to cruise altitude and leveling off, you should delay fine-tuning the engine for 4 or 5 minutes. This allows the engine to adjust to the higher airspeed and the cooler airflow associated with the cruise portion of the flight. Engine temperatures should stabilize in this period of time and allow for a more accurate mixture adjustment. Leaning is best accomplished with a very slow retardation of the mixture control. The leaning process in cruise configuration should be done at 75% power or less. One final note regarding mixture. A very simple pilot check for the mixture setting itself is the idle shutdown check. At shutdown, reduce the RPM to low reading, perhaps in the 700 range, and close the mixture. If the setting is all right, you should get a slight rise in RPM before spool down. If no rise, the mixture is too lean. If there is a significant rise, the mixture is too rich. The engine oil system is the wet sump type with a spin-on oil filter available as an option. The standard filter screen requires more attention, and it is recommended that oil be changed with this installation every 25 hours. Otherwise, the concerns to be checked are the same in each system. The manufacturers recommend the use of ashless dispersant oil. SAE 20W50 or SAE 15W50 are acceptable for all temperature ranges. Sludge is a product of improper use of the mixture, untimely oil changes, and intermittent stops and starts before there is a significant temperature rise. Detergent oil manufactured today supposedly will not desludge an engine to the point that the ports and galleries will be clogged, but this recent accident report suggests that there may be exceptions. Quote, "The engine failed on takeoff. Aircraft nosed over on landing. Use of detergent oil caused oil screen to clog." Unquote. The sump has a capacity of 6 quarts. However, 7 may be installed when the oil and spin-on oil filter are changed because of the filter requirements. The oil level should not be allowed to fall below 4 quarts at any time. Aside from being a lubricant, oil has another very important function. It removes the excess heat fast enough from the internal parts of the engine to maintain a safe operating temperature. If the level is allowed to drop too low, this cooling process begins to deteriorate, and the internal hot spots may operate at higher than normal temperatures. These high temperatures in the hot areas of the engine will subject the oil to coking and oxidation. Coking tends to dirty the oil with carbon particles, while oxidation causes the oil to break down and thicken. A full flow oil filter will remove most of the carbon particles, but nothing can be done about oxidation except draining and replacing the old oil with clean oil. Both of these phenomena have a destructive effect on the engine, and failure to manage the lubrication of your engine properly can be very expensive and is potentially dangerous. For normal engine operation, it is recommended that the full flow oil filter be changed every 50 hours and the oil every 50 hours. We recommend that careful attention be paid to the quality of the oil, and if you have any reason to believe that coking or oxidation are beginning to affect your oil, that you perform these services at shorter intervals. In calendar time, 4 months should be the maximum time between changes without regard to flight time. Infrequent flight is an enemy of the oil in your engine. Condensation will permit moisture to collect, and if engine temperatures are not raised frequently to evaporate it, a corrosion process will result. Operating at too rich a mixture setting will deposit lead sludge in the oil, and the filter will not remove it. This, among other things, promotes sticking valves, so the oil must be drained. Clean oil is essential to long engine life. However, the oil change job isn't done until all security provisions are in place. Quote, "Aircraft was in level cruise at 5,000 feet MSL approximately 10 minutes after takeoff, when a total loss of engine oil pressure was observed. Power was reduced to idle immediately, and a precautionary landing at a nearby airport was completed within 4 minutes from first detection of power loss. Oil drain failed." Unquote. The pilot did a good job here, and we don't know why it failed. But it is worthy of note that there have been many quick drain installations that used an improper drain. These drains should be specific to the airplane and not purchased from your helpful hardware man. In our walk-around, the engine accessory mounting flanges should always be checked carefully. You really can't afford to lose them. Quote, "Found oil cooler right side mounting flange broken, attached to aircraft on right side with only 2 holding holes rather than the 6 on that side. The left mounting flange was found whole and secured. Cause for this was probably vibration." Unquote. About 1/3 of the engine heat is dissipated with the oil and oil cooler, and in the event of an oil temperature rise, the cooler should be checked after a flight by placing a hand on the cooler itself. If it isn't hot, it isn't working, and the first check should be the vernitherm. It may be worn and require replacement. In discussing engine operation and overall engine care, cold weather operations must be considered. The cold weather start is extremely trying for your engine. This is a time in which it undergoes a very drastic temperature change in a very short time span. It is a time in which the need for lubrication is as great as we will find in any phase of engine operation. Unfortunately, it is also a time in which we do not have very effective lubrication. For this reason, we must stress the use of preheat or a warm hanger for cold engine starts. Generally, anything below 20 degrees Fahrenheit would warrant the use of preheat if no hanger is available. This assumes that the engine has completely cooled and has been sitting in this condition for a considerable period of time. When starting a cold engine, it is recommended that oil temperatures be brought up to 75 degrees Fahrenheit, or roughly 24 degrees centigrade, prior to operating the engine above 1200 RPM. This will ensure that the oil's viscosity is at a point where a higher RPM is not harmful in terms of adequate lubrication. Remember that without the oil circulating, some very expensive metal is rubbing together and chewing up metal surfaces and dollars simultaneously. Just to make life more difficult, you should know that under no circumstances should you let your engine idle under 1000 RPM anytime, unless you enjoy plug changes, overheating, and low batteries. A cold weather problem is that of congealed oil. This is a situation in which the oil in the sump is very thick and will not flow fast enough to replace the oil which is going through the oil pump and through the system. As the pump picks up cold oil, the oil which replaces it does not flow fast enough. Today's multi-viscosity ashless dispersant oils have alleviated this problem to some extent, but a combination of circumstances could overcome the scientific efforts of the petroleum industry. In a condition of congealed oil, the pump begins to cavitate and draws in air. When the air begins to flow through the system, oil pressure will drop to 0 and lubrication will be non-existent. If allowed to continue, your engine will very shortly have the value of molten metal. If you use preheat or have a warm hanger, you won't have a problem with congealed oil during cold weather operations as long as you don't delay engine start and do retain the heat. This does not release you from the obligation to exercise due caution and care, to monitor engine instruments after the engine start and prior to takeoff. Congealed oil will be a problem for the pilot who takes very little time between engine start and takeoff in cold weather operations. Just about the time that the oil pump cavitates, the oil pressure drops to 0, and the temperature begins to rise, you will probably be in the initial stages of climb out, the worst possible time for the single engine pilot to experience a sudden engine stoppage. The resulting trauma, even if it is only emotional, will make the time saved by careless shortcuts seem like a high-priced purchase indeed. One final word about oil. Multi-viscosity oil is very convenient. It enables you to be consistent in grade and quality the year round, but it is quite expensive. For the average personal pilot, it offers protection at high and low temperature extremes. This, however, may not be necessary if simple guidelines relative to preheat and temperature management to avoid high engine temperatures are observed. The proper weight mineral oil will function very well, and over the life of your engine could save you a great deal of money. A note of caution, however: you must always use aviation-grade oil. Automotive oil will not function in the higher temperatures of an air-cooled engine. Even if you follow the best possible operating procedures, you will certainly meet engine problems that will cause concern. If you have monitored oil consumption carefully in order to establish a normal pattern, you will find that sooner or later it will begin to rise. Or your mag checks indicate excessive drop or separation. Or you may experience an unexplained engine roughness. Or perhaps you think the engine is getting tired and want to know more about it. Some of the additional ground checks that will give you information are removal and cleaning of the spark plugs, checking the oil filter at oil change time, and running a compression check. The first two you may do yourself if you have the tools and a good mechanic looking over your shoulder. The compression check should be accomplished by a qualified mechanic. The full flow oil filter checked each 50 hours will tell you much about your engine. It often provides the first clues to an imminent catastrophic failure in time to prevent it. When the filter is removed and opened up, it should be thoroughly checked for contaminants, particularly metal. A small magnet should be used to search for ferrous metals, and if suspicion arises, it might be wise to wash the filter with solvent and check the residue with a magnet. If you are doing this yourself, and you find any indication whatsoever of this problem, hold the evidence and get your mechanic to check it. A typical SDR worthy of note makes a strong case for regular oil changes and a thorough filter check for metal and contaminants. Quote, 50-hour oil and filter change and compliance with AD 80-04-03R2 Amendment 39-5893, metal chips were detected in oil filter. On inspection of hydraulic tappets, number 2-cylinder exhaust tappet was severely spalled and chipped. Cam lobe was also badly spalled and grooved, unquote. This was the H2AD engine introduced on the 172N in 1977. It was designed to operate on 100 low lead and was particularly prone to spalling problems. It was an embarrassment to both Lycoming and Cessna. After extensive modification on engines in the field and a factory improvement starting with serial number 7967, the problem was helped. However, the engine is still regarded with suspicion in some circles, perhaps unjustly. The replacement E2DJ was introduced in 1981. The spark plug check will tell a great deal more than the condition of the plugs, but removal, storing properly, examining, cleaning, gapping, and reinstalling must be done properly or problems can arise. They must be removed properly or they can be damaged. The location must be noted so that they may be rotated back in proper order and correct analysis be made of the proper cylinder. Cleaning and gapping requires some technique, and reinstallation must be in the proper cylinder. Also, plugs must be properly torqued. Before cleaning the plugs, they should be examined closely. Each tells its own story.
These are some of the things to look for when examining the firing end of a spark plug. This is a worn-out spark plug. The ground and the center electrode are going to wear due to normal use. The ground electrode is less than half of its original thickness. The spark plug should be replaced. This is a lead-fouled spark plug. It has hard clinker-like deposits, and that's metallic lead on the spark plug. It's caused by inadequate fuel vaporization, high concentration of tetraethyl lead in the fuel, and engine operations at too cold of a temperature. If you have this situation, remove all that lead deposit and reinstall the spark plug. If it's excessive, install a new spark plug. This is an oil-fouled spark plug. It has a wet, oily carbon deposit on it. It can be caused by a broken piston ring, worn piston rings, an engine that's still in the break-in period, the impeller seal on a supercharger, excessive valve guide clearance, and so on, anytime you're going to get excessive oil in the engine. Clean the spark plug and put it back into service. This is a carbon fouled spark plug. It has a black, dull, sooty deposit on it. This can be caused by excessive ground idling. The idle mixture is too rich, or the spark plug is too cold. Check with your A&P mechanic on this to make sure that you have the proper heat range of a spark plug. If you've readjusted your mixture, you can clean the spark plug and reinstall it. This is a normal spark plug. It has a light brown to gray tinge on it. It looks in good condition as far as electrode wear. It's a matter of cleaning, regapping, and installing.
The compression check is a very important tool for determining the combustion efficiency of the engine. A mechanic will remove a spark plug and hook a compression tester through the spark plug hole to an air line to pressurize the cylinder to 80 pounds. There will be some loss of pressure, and he will now have two readings, 80 for one and the new pressure for the other. We may expect a reading of 75 to 78 psi to be very high. A normal range may be 67 to 75 psi. A reading below 60-80 is cause for some alarm, and we would suspect that the cylinder should be pulled from the engine for closer inspection. Another very effective procedure for troubleshooting the cylinder is the use of a borescope. A lighted scope is inserted through the spark plug hole, and the mechanic is able to see the interior of the cylinder and usually make an evaluation. Inevitably, you will confront the problem of TBO, or time before overhaul. You should know that this is a suggested or recommended time only. If oil consumption records and the checks mentioned above are performed by a qualified mechanic who gives your engine a clean bill of health, many owners would choose to continue operation until less favorable testing results appear. That is your option. If you choose this route, be very careful and monitor it closely. An exception might be a bulletin from on high, which says that a jigger in your engine, which you have never heard of, is pooping out badly and should have early attention. A teardown or perhaps an early overhaul is the prescription. Listen and heed. Somewhere in that bureaucratic maze is a fellow who knows what he is talking about. Finally, the day will come when you will have to replace the engine, and we should review the procedures to break in a new or overhauled engine, or when new or overhauled cylinders are installed. Use the recommended oil and stay with it for the full break-in period. Change oil and filter as recommended in the pilot's operating handbook, more frequently if you are operating in a time and place where the atmosphere is dirty. Every takeoff should be made at full power, and in a 172 the power may be maintained until you have reached cruise altitude. The placard for permitting 2700 RPM was originally proposed by the sales department at Cessna in the hopes that the increased performance would be attractive to potential buyers. We understand the technical people were opposed, but were pleasantly surprised to find it seemed to be having no effect on engine life. We have not seen the data that support this. Climb to a cruising altitude that will allow you to maintain 75% power, never less than 65%. This power is necessary for the breaking in or mating of the piston rings to the cylinder walls. The power should be maintained for all cruise operations during this break-in period. On extended cross-country trips, every 30 minutes or so, advance to full power for about 30 seconds and then return to your cruise settings. It will very likely be necessary to use 2700 RPM at altitude to obtain 75% power for cruise during this break-in period. On descents and approaches, always carry enough power to keep the cylinder heads warm. Temperatures should be maintained within a normal operating range. Conversely, you need to climb a little more shallowly with higher speeds to maintain adequate cooling. A brief explanation is in order at this point. Higher power settings are needed to develop the cylinder pressures necessary to push the rings onto the cylinder wall. The pressure has to be great enough to rupture the oil film and permit the ring to come into contact with the wall. This ring and cylinder wall contact has to be maintained until a smooth, compatible surface exists between the two. When this happens, the break-in period should be complete. It takes approximately 25 to 50 hours to complete this process if the above steps are followed. The break-in process should be completed in as short a time as possible. The only way to do this is with the higher power settings. The lower power will not provide enough cylinder pressures to push the ring hard against the cylinder wall, and the break-in period would then be extended over a long period of time. In the meanwhile, oxidation of the oil will begin to glaze and fill in those grooves. If the glazing takes place before the complete mating of ring to cylinder wall, the end result will be higher oil consumption. The only remedy in this case would be to hone the cylinders and install new rings. This could be very costly. High-speed descents with very low power create other enemies of engine life. In cold temperatures, these types of descents may lead to shock cooling, which may cause rapid contraction of metal parts. This will eventually lead to cracks on the cylinders, the spark plug holes, and any openings that are subject to stress and fatigue. This sets the stage for another phenomenon known as ring flutter. Ring flutter occurs when the compression rings are allowed to float within the ring grooves, leading to a gradual deterioration of the ring groove itself. This is caused by a low-power, high-speed descent in which there is not enough combustion force in the cylinder to keep the compression rings seated properly. When this deterioration occurs in the compression ring groove, oil consumption will begin to increase rapidly, and the compression efficiency will decrease. The inevitable result will be an overhaul of the engine in a very short time.